All right, strap yourselves in, because today we are going deep on wormholes.
Wormholes.
You've sent us a ton of stuff on this.
Okay.
Articles, research papers,
Yeah.
even some pretty out there cosmology.
Yeah.
You're clearly as fascinated by these things as I am.
Absolutely.
These theoretical tunnels through space-time. I mean, just the idea that these things could exist is...
It is pretty wild, right?
Yeah, it's wild. It's wild.
It really is.
I'm still trying to wrap my head around how a wormhole would even, how would it work structurally? What are we talking about here? We're not just talking about, falling into a black hole, right?
No, it's not just a black hole. It's more like a tunnel.
Okay.
With two openings.
Okay.
And those are called mouths.
Mouths, okay.
Connected by a narrow passage.
Okay.
Called the throat.
Oh.
And here's where things get a little complicated.
Okay.
For a wormhole to be traversable, it needs to be held open.
Okay.
And that's where exotic matter comes in.
Exotic matter.
Exotic matter.
That sounds like something straight out of Star Trek.
Well, it kind of is.
But what makes it so exotic?
Yeah.
And why is it so crucial for wormholes?
It's exotic because it behaves unlike anything we've ever observed. We're talking about matter with negative energy density.
Negative energy density.
This isn't just some kind of hypothetical concept, by the way.
Right.
This stuff pops up in areas like the Casimir effect, where empty space exhibits negative energy density.
Wait, so empty space can have negative energy?
That's exactly right.
That's mind-blowing.
It's pretty amazing.
How does that tie back to keeping a wormhole open?
Well, think of it this way.
Okay.
Gravity normally pulls things together.
Yeah,
right?
Yeah, of course.
But negative energy density would have the opposite effect.
Okay.
It would push things apart.
Okay.
And so it would counteract the intense gravitational forces that would try to collapse a wormhole.
So exotic matter would act like scaffolding.
That's a great way to put it, yeah.
Holding the wormhole open.
Exactly.
I mean, that's just crazy.
Yeah.
So even if this exotic matter actually exists,
right,
we're a long way from actually being able to harness that, right?
Oh, yeah.
I mean, we're talking about
that's right.
Engineering on a cosmic scale.
Absolutely. But the fact that the math allows for it,
Yeah.
The fact that these solutions emerge from Einstein's equations,
Right.
is what keeps physicists exploring these possibilities.
Exploring, and some of those possibilities are truly mind-boggling.
They are.
We're talking
right,
time travel, alternate universes.
Yeah.
I mean, this is stuff that used to be purely in the realm of science fiction.
That's right.
So tell me about that.
Well, one of the most fascinating aspects, I think, of wormholes is this potential connection to these things called closed time-like curves.
Closed time-like curves.
And these are paths through space-time that loop back on themselves.
Oh, wow.
And potentially allow for travel.
Okay.
Not only through space, but through time as well.
Okay, now my brain is officially starting to hurt.
Yeah, I hear you.
But before we get too lost in time paradoxes,
right,
let's maybe ground ourselves a bit.
Okay.
You mentioned that wormholes are connected to some pretty advanced concepts.
Right.
In physics, like the multiverse.
Right.
So how does that work?
Well, so there are different multiverse models.
Okay.
But some physicists theorize that wormholes could act as bridges between these separate universes.
Oh, wow.
Imagine a vast network of universes.
Okay.
Each with its own unique properties.
Right.
Connected by these cosmic tunnels.
That is a lot to process.
Yeah, it is.
But even if it's all theoretical,
right,
the idea of wormholes linking different realities is...
It's amazing, isn't it?
It's incredible.
It's incredible.
Yeah.
And this is where I think the study of wormholes gets really, really interesting.
Okay.
Because we're not just talking about potential shortcuts across the universe.
Yeah.
We're talking about gateways to entirely different realities.
Wow.
And it challenges our very understanding of space, time, and the nature of existence itself.
So these wormholes aren't just about getting from point A to point B faster.
No.
They could completely rewrite our understanding of the cosmos.
Absolutely. That's exactly right.
Wow.
And that's why, despite the immense theoretical challenges, the study of wormholes continues to fascinate physicists and capture the public imagination.
I'm starting to see why you find this so fascinating.
I do. It's fascinating.
So speaking of challenges, one of the biggest we've talked about is this exotic matter.
Yeah.
It's theoretical.
Right.
But there are some tantalizing hints that it might not be entirely out of reach.
That's right.
Right. So, as I mentioned earlier, the Casimir effect provides a real-world example of negative energy density.
Okay.
Though on a much smaller scale than what would be needed for a wormhole.
Right, of course. Yeah. Of course. Yeah. But as our understanding of quantum physics deepens, who knows what other strange properties of the universe we might uncover.
So while creating a traversable wormhole might be far beyond our current capabilities, the very fact that it's mathematically possible and that we see these hints of the necessary ingredients in the universe is pretty incredible.
Yeah. I agree.
I'm definitely starting to see why you find this topic so fascinating.
Oh, yeah. It's a good one.
So where do we go from here?
Wow.
If we haven't directly observed a wormhole yet, how are scientists trying to find them?
Well, that's a great question.
Yeah.
And there are a couple of really interesting avenues of research that I think are worth talking about.
Okay.
One avenue is looking for their subtle gravitational effects.
Okay.
A wormhole, even if we can't see it directly, would still warp space-time around it.
Okay, so kind of like how we infer the existence of dark matter.
That's a great analogy.
By observing its gravitational influence on galaxies and things like that?
Precisely.
Yeah.
So scientists are using a similar approach with wormholes.
Okay.
And they're analyzing data from gravitational lensing, where light from distant objects is bent by the gravity of massive objects in the foreground.
Okay.
If a wormhole were to lie along the path of that light, it would create a very distinct distortion pattern.
So we're basically looking for these tiny little hiccups.
That's a great way to put it.
Yeah.
Yeah.
In the fabric of space-time.
Right.
That could betray a wormhole's presence.
Exactly. It's an incredibly subtle effect.
Yeah.
But with advancements in our instruments and our data analysis techniques, it is a possibility.
Okay.
Another method that you mentioned earlier was studying high-energy astrophysical events, like black holes and neutron stars.
Right.
So what makes these environments so promising for wormhole research? Well, these are regions where gravity is incredibly intense.
Okay.
Potentially creating conditions where space-time could be warped enough to form a wormhole. Think of it like stretching a rubber sheet. Where you stretch it, the more likely it is to tear or to form a hole.
So these extreme environments might be the cosmic rubber sheets.
Exactly. That's a great way to put it.
Where wormholes could potentially form.
Yeah. And by studying the emissions from these objects, especially in the form of gravitational waves, scientists hope to find signatures that match what the theoretical models predict for wormholes.
So I'm starting to see how the search for wormholes is really pushing the boundaries.
It is.
Of our observational capabilities.
It really is.
But let's shift gears for a moment and delve back into some of the theoretical implications.
First,
We talked about time travel, but
that
that opens up a whole can of worms.
It does.
Pun intended.
Yeah, of course.
About paradoxes, right?
Paradoxes, exactly.
Yeah. So
a big one.
So tell me about those.
Well, so one of the most famous ones is the grandfather paradox.
Okay.
Where you go back in time and prevent your grandparents from meeting, leading to your own non-existence.
Of course,
Right? So this paradox highlights the potential conflicts between time travel and causality, the relationship between cause and effect.
Right. Okay.
So if wormholes could facilitate time travel, how do we reconcile that with these seemingly inviolable laws of cause and effect?
Yeah, that's a great question.
That's a big one.
Yeah, it is.
It's a question that has puzzled physicists and philosophers for decades.
I bet.
Some theories suggest that time travel might only be possible in a way that avoids paradoxes.
Okay.
Perhaps by splitting off into alternate timelines.
Okay.
So going back in time wouldn't change our past. But instead, it would create a new divergent timeline.
Okay, so it's almost like creating a copy. Yeah, like a branching.
That's reality.
Exactly, a branching.
And then you go down one branch.
Yeah, exactly.
And the other one continues on as it was.
Exactly.
Okay, I like that.
Yeah, it's a cool idea.
Yeah.
Another idea is that the universe has a built-in mechanism for preventing paradoxes.
Right.
A sort of cosmic censorship that ensures consistency.
So even if you tried to create a paradox, the universe would find a way to prevent it.
Yeah, it would just sort of step in and say, nope, not going to happen.
That's pretty wild.
It's pretty wild stuff.
Yeah.
But, it's all very speculative, of course.
Yeah.
But these are the kinds of thought experiments that physicists engage in when grappling with these mind-bending implications of time travel.
It's amazing to think that something as seemingly straightforward
I know, right?
as a tunnel through space-time
Yeah.
could lead to such profound questions
It's profound.
about the nature of time and reality itself. It really highlights how interconnected physics is.
Yeah.
The study of wormholes draws on insights from general relativity,
Right.
quantum mechanics,
Yeah.
cosmology.
Yeah.
It's a true intersection of some of the most fundamental areas of physics.
And it's still such a young field of research. Who
Who
knows what breakthroughs await us as we continue to probe
Exactly.
the mysteries of wormholes.
That's the beauty of science,
Yeah,
right?
yeah.
It's a never-ending quest for knowledge.
Right.
And with every answer we uncover,
Yeah.
new questions arise.
Yeah, it's true.
The study of wormholes is a prime example of this ongoing journey of discovery.
I think our listeners probably feeling a little overwhelmed by all this information.
It's a lot, right?
That is a lot to digest.
It is.
Yeah. So before we move on,
Yep.
is there anything you'd like to reiterate or emphasize
Sure.
about what we've covered so far?
Well, I think
Right.
a key takeaway, is that wormholes, while rooted in theoretical physics, have a real impact on how we view the universe. They push us to consider possibilities that would have been unimaginable just a few decades ago.
Yeah, we've talked about the mind-bending implications for time travel and multiverses.
Right.
But even setting those aside,
Yeah.
the idea of a shortcut through space-time,
Right.
it's revolutionary in itself.
It is.
I mean, it challenges
It really does.
our most fundamental assumptions about distance and the limits of exploration.
Exactly. And it's fascinating to think about the technological advancements that would be necessary to even contemplate interacting with a wormhole.
Right.
I mean, we're talking about manipulating energy and gravity on a scale that dwarfs anything we've ever even attempted.
It's a good reminder that our current understanding of physics might just be scratching the surface.
Oh, absolutely.
Who knows what incredible discoveries await us as we continue to probe the universe's deepest secrets.
What I find particularly exciting is how the study of wormholes is intertwined with other areas of cutting-edge research. Advances in quantum gravity, string theory, even information theory could hold the key to unlocking some of the mysteries surrounding wormholes.
So even if we never actually manage to create or traverse a wormhole, the pursuit itself is driving scientific progress across multiple disciplines.
Absolutely. It's pushing the boundaries of our knowledge and forcing us to confront some of the biggest questions in physics. Cosmology. Even philosophy. What is the nature of time? What are the limits of causality? Do other universes exist? These are questions that have intrigued thinkers for centuries. And the study of wormholes is bringing us closer to potential answers.
I think it's safe to say that our listener has a whole new perspective on wormholes now.
Yeah, I hope so.
You know, they've gone from a science fiction concept to a serious topic of scientific inquiry, with real implications for how we view our place in the cosmos.
And that's the power of curiosity, isn't it?
Yeah.
It drives us to explore the unknown, to challenge assumptions, and to expand our understanding of the universe and ourselves.
So to wrap up this deep dive, what's the one message you'd like to leave our listener with? What should they take away from this journey through the mind-bending realm of wormholes?
I would say this: embrace the wonder. The universe is full of mysteries, and the more we learn, the more we realize how much we don't know.
It's true.
The study of wormholes is a testament to the boundless capacity of human curiosity and imagination. It's a reminder that even the most seemingly outlandish ideas deserve exploration. For they might hold the key to unlocking the universe's deepest secrets.
Beautifully said. And on that note, we'd like to thank you, dear listener, for joining us on this incredible adventure through the warped and wonderful world of wormholes.
It's been fun.
We hope you've enjoyed the ride and perhaps even felt your own mind bend a little along the way.
A little bit.
And who knows, maybe someday the science fiction of today will become the science fact of tomorrow.
Maybe, yeah.
Until then, keep exploring.
Keep exploring.
Keep questioning.
Yes.
And keep looking up at the stars with a sense of wonder.
That's where the magic is.
That's where the real magic lies.
Well, I think a key takeaway is that wormholes, while rooted in theoretical physics, have a real impact on how we view the universe. They push us to consider possibilities that would have been unimaginable just a few decades ago.
Yeah, we've talked about the mind-bending implications for time travel and multiverses.
Right.
But even setting those aside,
Yeah.
the idea of a shortcut through space-time is revolutionary in itself.
It is. It is.
It challenges our most fundamental assumptions about distance.
Absolutely.
And the limits of exploration.
Exactly. And it's fascinating to think about the technological advancements that would be necessary to even contemplate interacting with a wormhole.
Yeah.
And we were talking about manipulating energy and gravity on a scale that dwarfs anything we've ever even attempted.
It's a good reminder that our current understanding of physics might just be scratching the surface.
Oh, absolutely.
Who knows what incredible discoveries await us as we continue to probe the universe's deepest secrets.
What I find particularly exciting is how the study of wormholes is intertwined with other areas of cutting-edge research. Advances in quantum gravity, string theory, even information theory could hold the key to unlocking some of the mysteries surrounding wormholes.
So even if we never actually manage to create or traverse a wormhole, the pursuit itself is driving scientific progress across multiple disciplines.
Absolutely. It's pushing the boundaries of our knowledge and forcing us to confront some of the biggest questions in physics, cosmology, even philosophy.
Right, like what is the nature of time?
Exactly.
What are the limits of causality? Do other universes exist?
These are questions that have intrigued thinkers for centuries.
That's right. And the study of wormholes is bringing us closer to potential answers.
I think it's safe to say that our listener has a whole new perspective on wormholes now.
I hope so.
They've gone from a science fiction concept to a serious topic of scientific inquiry with real implications for how we view our place in the cosmos.
And that's the power of curiosity, isn't it? It drives us to explore the unknown, to challenge assumptions, and to expand our understanding of the universe and ourselves.
So to wrap up this deep dive, what's the one message you'd like to leave our listener with? What should they take away from this journey through the mind-bending realm of wormholes?
I would say this. Embrace the wonder. The universe is full of mysteries, and the more we learn, the more we realize how much we don't know. The study of wormholes is a testament to the boundless capacity of human curiosity and imagination. It's a reminder that even the most seemingly outlandish ideas deserve exploration, for they might hold the key to unlocking the universe's deepest secrets. Beautifully said. And on that note, we'd like to thank you, dear listener, for joining us on this incredible adventure through the warped and wonderful world of wormholes. We hope you've enjoyed the ride and perhaps even felt your own mind bend a little along the way.
A little bit.
And who knows, maybe someday the science fiction of today will become the science fact of tomorrow.
Maybe, yeah.
Until then, keep exploring, keep questioning, and keep looking up at the stars with a sense of wonder. That's where the real magic lies.